Hello, I'm Carl Mungan from the U.S. Naval Academy, and I'm delighted to join you today for this virtual meeting. So, let's consider a bead of mass m that can slide on a rough rod with a coefficient of kinetic friction equal to mu. And let's suppose that this rod is in gravity-free space. Now, suppose that we have a motor which can drive the rod to rotate at a constant angular speed about its midpoint, regardless of where the bead is located on the rod. So we'll call the angular speed of the rod omega, and we'll assume the motor is variable speed, so we can adjust omega to be any fixed value you want. And we have end stops to prevent the bead from sliding off the two ends of the rod. Now, let's work in the rotating reference system of the rod so that we simply have 1D motion along the axis of the rod, which we'll call the x-axis, with x equals 0 at the center of the rod. This means that we're working in a non-inertial reference system. Consequently, there'll be a centrifugal acceleration, omega squared x, that's equal and opposite to the centripetal acceleration, and a Coriolis acceleration, 2 omega times x dot. In other words, just the magnitude of twice the velocity crossed with the angular velocity. And I'm using over dots to denote time derivatives. So for the example shown here in this figure, we can see that x, the position of the bead, is less than 0, and the velocity x dot of the bead is positive if the bead happens to be moving to the right at that instant. Now finally, let's add in a pair of ideal elastic bands, meaning they're massless, they perfectly obey Hooke's law, and they have 0 relaxed length, which are attached in such a fashion that they always pull the bead back toward the origin. And let's let the spring constant of each elastic band be kappa. And we will have small slits on the bead so that the bead can pass over the elastic bands that pass from one side to the other of the rod. Okay, we'll start the bead at the origin. X sub 0 equals 0 will be the initial condition. And the rod is rotating, and we're going to give the bead an impulsive radially outward push so that x dot sub 0 is, say, positive. And the question is, what are the possible resulting motions of the bead if the rod has different angular speeds omega? Well, there are 3 possibilities. See if you can think of what those 3 possibilities might be. Possibility number 1. At low angular speeds, the bead will eventually return to the origin due to the undercritical or overdamping of the motion. The damping results from the kinetic friction. But remember, I said the rod was in gravity-free space. So the friction arises because there's a normal force due to what, given that the bead has no weight? Due to the Coriolis force, which is perpendicular to the axis of the rod. And so that is in the correct direction to exert a normal force. It's V cross omega, so that will be in the horizontal direction perpendicular to the axis of the rod. Possibility number 2, if we go to the opposite extreme of very large angular speeds, the bead will slide outward until it hits the end stops, no matter how far away those end stops are. And what is it that will cause the bead to do that? What force? The centrifugal force, right, which causes the bead to be flung outwards. Finally, this means that at some intermediate crossover angular speed, the bead will move away from the origin to a new equilibrium position. And my question here is that new equilibrium position stable, unstable, or neutral? It'll turn out to be neutral. So those are the 3 possible motions of the bead. To see how this comes about, let's apply Newton's second law mathematically. So the mass times the acceleration will be given by the sum of three forces. We've got the restoring force due to the two elastic bands, which gives us minus 2 kappa times the position x of the bead displaced away from the origin. We've got the outward centrifugal force, which is the mass times the centrifugal acceleration omega squared x. And then we've got the kinetic friction, which is minus mu times the normal force given by the Coriolis force 2m omega x dot. Notice that this direction of this frictional force will always be opposite the velocity x dot of the bead, as we expect for kinetic friction. Now, on the other hand, there's no static friction because the normal force, that is the Coriolis force, equals 0 whenever the velocity x dot is 0. Okay, so we notice that there are two terms proportional to x, so we'll collect them together by defining omega naught squared equal to 2 kappa over the mass minus omega squared, and we'll define a damping coefficient beta equal to mu times omega. So both beta and omega naught have units of per second. And consequently, we end up with this red differential equation here, second order linear differential equation. And you'll notice that this is the standard form of a linearly damped oscillator equation. So we know how to solve it. In particular, whether we get under, critical, or over damping depends on the size of beta compared to omega naught. So if beta is less than omega naught, then we have weak or under damping. So if we go back and substitute in what our expression for omega naught is, we will find that omega turns out to be less than some critical angular speed, which I've called omega c star, which is determined by the spring constant kappa, the mass of the bead m, and the frictional coefficient mu. We'll get critical damping if omega equals the critical angular speed, and we'll get over damping if omega is larger than this critical angular speed, but only up to some angular speed, which I call omega c, a crossover angular speed to a different kind of motion. Now, eventually, omega gets large enough that omega naught squared becomes 0. And we can see from this equation that that happens when omega, being omega sub c, equals twice kappa divided by n. That's also the critical value, omega c star, in the absence of friction if mu equals 0. Now, if omega is greater than omega c, we do not get over-damped motion, but instead the bead will slide radially outward until it hits the end stops, which is the second possibility I mentioned before. But at the crossover value, our differential equation simplifies to the mass times the acceleration simply equals the frictional force. And therefore, writing the acceleration as the time derivative of the velocity, we can see that we can easily solve for the velocity by separating and integrating to get that the velocity will exponentially damp away. And so the bead will slide, but it'll gradually come to rest at a new equilibrium position. And we can see here that the new equilibrium position must be neutral because the elastic and centrifugal forces will balance at any value of x, provided the angular speed is omega sub c. Now, taking this boxed equation for the velocity, we can integrate it again to find the position as a function of time. And so we find what the new equilibrium position x sub infinity is. I called it x sub infinity because it takes an infinite amount of time for the bead to actually reach that final equilibrium position. And as we expect intuitively, that final equilibrium position is larger if we started with a bigger initial velocity, or if we had a bigger mass, meaning more inertia, so that it goes out to a further position. On the other hand, if we have a larger frictional coefficient, then it'll stop at a shorter distance. Or if the spring constant is larger, that will also prevent it from going out to a further distance. So this expression for the new equilibrium position is exactly in the form we might expect. So here's a graph of the displacement of the bead for 3 different values of the angular speed. I've chosen all the parameters for simplicity to be 1. The mass is 1 kilogram. Twice the spring constant is Newton per meter. The frictional coefficient is 1. The initial velocity in the radial direction is a meter per second. That means that the critical angular speed omega sub c star is 1 over root 2 meters per second, and that the crossover angular speed is a meter per second. So for very small values, we get underdamping. So say omega is 0.1 radians per second, we get the blue curve indicated here. We get overdamping when we're between omega sub c star and omega sub c. So for instance, at 0.9 radians per second, we see that it returns slowly to the origin without oscillating. And finally, if we're at the crossover angular speed, then it moves out and stops at some position beyond the origin. So in this case here, it stops at 0.5 meters away from the origin. Okay, if you want to see more details on this, I have a paper in this month's issue of the Physics Teacher, which is actually a letter commenting on an article from the May issue, which discusses some of these points, but I correct some errors in that paper and bring out some additional aspects not indicated in that paper. So thank you for your attention.